Okay, good. That is the history. Okay. And what you have to know, there's something important about capacitors that you have to memorize. No? Okay. Let's write it down. Capacitors are devices that store electrical energy. They are made of two charged met, metal objects conducting two charged conducting objects that are electrically insulated. One of them is charged positively, charged with positive charges, and the other is negative, positive charges plus Q, and the other is negative charges minus Q. Okay. Capacitors can be quantitatively characterized by a quantity we call the capacitance, defined as, how is capacitance defined? You have to memorize that, okay? Defined as, here you go, capacitance C, the amount of charge in one of the capacitors, okay, divided by the potential difference between them. This is a very important quantity that you have to memorize. Okay? If you charge this capacitor to 10 volts, okay? And then you discover that there is an electric potential difference of, you discover that you have a charge, right? Not electric potential difference. Let's say a charge of 1 microcoulomb, okay? So let's say, example, let me do an example here for you. Simple numerical example. Suppose you charge a capacitor. How much charge? Yeah, here can see this one can hold up to 50 volts. Can be charged up to 50 volts. Okay, more than 50 volts, you can damage it or even get it to explode. Suppose you charge a capacitor to 10 volts. Okay, and it becomes charged, and it holds. Suppose a capacitor holds a charge of 1 microcoulomb, like that, and a potential difference and an electric potential of 10 volts. 10 volts. Find its capacitance. Okay? Here, let's put millicoulombs, not micro. Let's put millicoulombs, so you can have a easier problem. What's going to be the capacitance of this capacitor? Yeah, just substitute the numbers there, okay? So here you go. Here is gonna be 1 millicoulomb upstairs, and downstairs is gonna be 10 volts. Okay, you do the math. What do we get? You get 10 to minus 4 coulomb per volt. Okay, 10 to minus 4 coulomb per volt. This unit appears so much, and it's so important. This unit appears so much in physics that we call it the farad. Abbreviate that by the letter F. Okay, that's the unit of capacitance. This capacitor that I'm holding has a capacitance of 470 microfarad. Okay, so I'll write that down here for you. The capacitor I am holding has a capacitance of 0.47 millifarad or 470 microfarad. This other one here, let's see, the brown capacitor. Let's see if it has a capacitor. Yeah, it doesn't. Yeah, the brown capacitance I showed to you, brown capacitor, the blue capacitor, right? The blue polarized capacitor I showed you has a capacitance. Okay, the brown capacitor has a capacitance of. I am suspicious that this number is not correct, but I'm gonna write that down for you anyway. It seems too much. Huh. It says here is 0.047. Seems too much of a capacitance. Okay, but that's what it says here. It seems that this guy is also a polarized capacitor because it has a negative symbol here on the right side. Okay. And then I'm going to show to you how we can calculate the capacitance of a capacitor in other ways. Okay, let's have our break first, and it's 6:03 right now. We come back 6:18. Okay, I see you in 15 minutes. Okay, oh boy, again. Ay, 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 ay. Alright, good. So here goes. So you got the definition of capacitance, and now we are going to do some examples. Okay, so let's start with the simplest of them. I start with the, oh yeah, let's start with the parallel plate one. Okay, we're going to start calculating the capacitance of the parallel plate. We already know that's the definition of the capacitance. Q divided by V, or Q divided by delta V. Okay? And we calculated what is the electric potential between two plates. Okay, so what we are doing here, let's go back here. We are going to calculate the capacitance of this configuration that you're seeing right in here. Okay? So let's put this way. I'm gonna put this way. Given two parallel plates separated by a distance d. Okay, and two circular plates, circular planar plates, two metallic, don't forget, two metallic circular plane, two metallic discs, okay, better, separated by a distance d and having an area A. Okay, find two. Let's see. We got here right in a different way. Okay, two metallic discs of same size form a capacitor. If the two discs, if the two discs are separated by a distance d, and have an area A, find their capacitance. Okay? The material, the dielectric between them is air. Okay, so that's a solution. Okay, so to find the capacitance, we are going to start with the definition of capacitance. Okay, it's something like that. And we also know from previous experiment that the electric potential between the two plates is going to be given by, let's say, a constant times the separation between the two plates. Do you remember that? The electric potential is linear with the distance, right? Now, there is a way, well, what we should do, we should go back to the equations, right, that we derived for the electric potential of two plates. Or even better, just remember that, here you go, just remember that what? That the electric field is what? Is given by the, dV dx, right? Remember that? dV dx. What else? Actually, it's minus, right? It's minus dV dx. But you can drop the sign later on. Remember also that for two parallel plates, this electric field was given by what? Do you remember what was this electric field given by? Is what? Sigma, remember that? By epsilon naught, right? Epsilon naught. Do you remember this result? Let's see. Do I have to remind you? Here you go. We calculated the electric field. We calculate the electric field between two plates between one, the electric field of a single plate, right? Using Gauss's law. And we're just confirming what, here we go. That's for that must be this way. Sigma, let's see. Point charge, ring rod, disk. Okay, summary. This is a summary. Let's see. Disk. No match? Doesn't make any sense. Okay, let's go. Let's try it again. Disk. Okay, finally. Calculate this. Okay. Of radius disk. And should be greater. Why are we getting? Is it a disk? That's not the one, definitely. Definitely this one is not the one. Disk resolution. Oh yeah, X much. Okay, that's the one right in here. Okay, but that's for just one disk, right? Just one disk. If you put a second disk with a different charge in there, here you go. That's what we got. E equal before, right? Let's here write that down, right? K is what? 4 pi epsilon, oops, epsilon naught. That's what K is, right? Here you go. The 2 cancels out with the 4. The pi combines with the r square and becomes a. The area of the circle, right? But that is the electric field just for one disk, one of the disk. If we, okay, that's the electric field. The electric field for a single disk is, right? Calculated before. Calculated before. Okay? So if we do Q divided by A, it becomes sigma, which is the surface charge density. And we have this half in here that we do not have here. Why is that? Because this one is for a single disk. However, if you combine one positive disk with a negative disk, the electric field inside the two disks are going to add to each other. And this half is going to disappear. Okay? If we combine the above disk with a second one that has an opposite charge, okay? The electric field, the E field in the region between the two plates becomes what I wrote here for you. So just to remind you how I got that. Okay? Now, from this result, we can find out the electric potential between the two plates, okay? And by the way, just a reminder, this V here is in reality, okay? It's better, it's easier. C is always positive, okay? So both the Q and the V must be a magnitude here. Here you go. It's better to put magnitude here so you don't keep on getting negative capacitance. Okay? So from the above, we can find out the electric potential. V is going to be magnitude of V is going to be, EX. Okay, but we want to know the electric potential difference between the two plates. If the two plates are separated by a distance d, then the electric potential is going to be ED. E is sigma over epsilon naught. Consequently, that was going to be your electric potential between the two plates. So let's go ahead, substitute that right in here in the definition. Okay, I'm going to erase this one because it becomes redundant. Look what the nice thing that happens. You don't need to know what the electric charge is. Okay, substituting the above in the equation for the capacitance, the above in the equation for the capacitance, we find the following. I gave you what D is, but I didn't give you what Q is. I didn't give you what sigma is. You know what epsilon is because it's a universal constant that has been measured over and over again. I'm going to rewrite this guy here. Recall that sigma is going to be the surface charge density, and by surface charge density, I mean magnitude of Q divided by the area. And what happens to the charge? It cancels out, right? The nice thing about the definition of capacitance is that all the time that we calculate the capacitance, the charge cancels out because the voltage is always directly proportional to the charge. And look what we get. We get that the capacitance is a function of the geometrical parameters of the capacitor. This equation, okay? This equation applies to any type of flat capacitor, any geometry of a flat capacitor. Whether it is circular, square, rectangular, triangular, etc. etc. Okay. Also, note that the capacitance does not depend on the charge nor on the voltage, but only on the geometrical parameters of the device. This happens to any capacitor, whether it is a parallel plate a cylindrical capacitor or a spherical one. Okay? So let's just summarize. Here you go. Summarize. First, we calculated the electric field of a planar charge distribution. Remember that, right? Then we calculated the E field of a planar charge distribution. Next, to another one, to another planar charge distribution with a opposite charge. Okay. Then we calculated, okay, in both cases, in both of the above cases, we found that the electric field is uniform. Then we calculated the electric potential. And found that it increases linearly with distance. Finally, we define an equation for the capacitance and calculated the capacitance of a parallel plate capacitor. Parallel plate capacitor. That's what we did. Okay? We can repeat the same for a spherical capacitor. We can repeat the same for a spherical capacitor. For a spherical and cylindrical capacitor. Spherical and cylindrical capacitors. Spherical and cylindrical concentric capacitors. Okay? Let's do that. Let's start with the find the capacitance of two spherical concentric capacitors of radii A and B. Okay, can do that too. Let's do that. So here goes. Solution. Solution. We start with the definition of capacitance. Here you go. In order for you to have the capacitance of a device, the device doesn't need to be charged. Those capacitors that I brought here, they already have a capacitance. They were not charged. They're not charged, but they did have a capacitance because they had this geometrical configuration. Okay? Although they had a capacitance, they didn't have any energy stored in it. They're not useful devices. A capacitor is not useful whenever it's not stored. But when you charge the capacitor, then it becomes useful. Okay? So that's the idea. Remember, for a spherical capacitor, right? The potential difference is just like that one of a point charge, right? K, Q, I'm gonna put magnitude here. KQ over R squared, right? That's how a spherical charge distribution, no, sorry, KQ over R, R squared is the electric field. All right, goes down with the distance. But let's go back here to our drawing. This is a spherical capacitor. Let me see. I don't have radius A and B there. I'm gonna use this one here. Yeah. Let's see. I'll get this one. Yeah. Here you go. Spherical capacitor. Here you go. Radius A and B. The inner one is positive, the outer one is negative, okay? So that R that you saw, remember, is the potential difference between this guy and this one. This surface and this surface. That's what it's all about. Okay, so what you're going to get is the R that you're going to get is going to be, B minus A, where B is greater than A. Substitute this relation for the electric potential right in here. And then what you get? P minus A over K. Or let's say 4 pi epsilon naught. Oh, 4 pi epsilon naught. Or pi epsilon naught. That's for the spherical capacitor. See, I got A over D. Let's see here. Let's just make sure you got it right. Yeah, A over D. Cylindrical surfaces. Let's see here. Spherical capacitor. Oh, I'm sorry, I made a mistake here. Okay, so here you go. Yeah, it's the way you do is like that. Here you go. We have an electric potential here, V sub A. Okay, so here you go. That's let me correct myself. Yeah, here you go. This what we have here. Don't forget that this is always is a difference in electric potential. Okay, always this is a difference in electric potential. So what this thing supposed to be? Supposed to be V over A minus V over sub V, B, right? Okay, the electric potential on the surface of A is going to be KQ divided by A, because this guy behaves just like a point charge. Okay, the electric potential at the second surface, at the surface of the outer spherical surface is going to be KQ divided by B. Okay, so go ahead. This is a better way of and now we can, here you go, come up with this equation here. KQ over A, KQ over B. Okay, Q cancel with Q. Here we go. Q cancel with Q. K can be, let's see, K can be, let's see what's the best way to do that. Let's take the common denominator here, B, right? KB minus KA, and we gotta get a AB here downstairs. Now put AB upstairs, put the K in evidence, and that's what we get for the capacitance of a spherical capacitor, which is completely different than what you saw before, right? Go. I can put like a K, let's see, 4 pi epsilon naught, put in terms of 4 pi epsilon naught here. Here we go. Again, this thing is a function of the geometric configuration of the device. Only the radius, inner and outer radius, radii, and the epsilon naught constant. 646. Let's do for the cylindrical capacitor. Okay, so find the capacitor to spherical concentric. Okay, find the capacitance. Find out two cylindrical concentric capacitors of radii A and B. Okay. So what was the electric potential for the cylinder, right? Did I do for the cylinder here? I know this one divided by R. No, I didn't. But let's just, which is the log, remember? The log. But let's get the exact electric field. I did that for this one. Here you go. I'm doing it from the very single capacitor. Here you go. I'm doing for the very beginning. Okay, Q enclosed. I put the sigma in there, ER. Okay, 1 divided by R. That's the electric field. Is the inverse of the distance, just like you have for the one-dimensional wire. Then if you want to find the delta V, you get the E dot ds, and then you should get log. Okay? So it's the electric potential between the inner surface and the outer surface. That's exactly what I get here. And then we go ahead and divide, right? Divide the Q by the delta V. That's what I'm doing here. Sigma epsilon naught A log B over A. And we still have an A here. Okay. Where this A comes from? The A comes from the electric field. Okay. And sigma is Q over the area of the capacitor. The area of the capacitor is 2 pi A, the circle, times the length L. Okay, the Q cancels out. And we end up with this capacitance. Okay, that depends on the length of the capacitor, of the cylindrical capacitor. So again, it's a function of the geometrical parameters of the device. Three important capacitors, planar capacitor, spherical capacitor, and cylindrical capacitor. So that, and they all, have the capacitance is always a function of the geometrical parameters. So you can stop here, 650. I'm going to just turn off my recording